Okay, hello everyone. I think we can begin. So before we get into the lecture, like a few administrative things as usual. So one, I think assignment 2 gradings, like grades are released. And tonight, I think 10 o'clock or 8 o'clock is the deadline for asking for a regrade. So I have one general comment about asking for regrade. So what I personally saw in A1 regrade is when you ask for a regrade, you have to give a justification why you want a regrade. Like you cannot let the TA understand like why you asked for a regrade, right? So there were a couple of regrade requests where the message is just a question mark. So that is definitely not the right way to ask for a regrade. And if you just put a question mark and the TA doesn't know what that means, he closes the regrade request, then that regrade request is done. So please give correct justification why you want a regrade. Okay. And I think the Kaggle competition has also started. We will release the test data on Friday so that then you can start testing your ideas, but the training data is available. So I would encourage you to download the training data, like create your validation set, do all your modeling with the validation set that you created, right? And remember that Friday is the hard deadline to form teams. So you cannot form teams after Friday. So everyone should be in a team of 3. So there's no exception. And like the only exception is if in the end there are 2 students in the class without a third person. Okay, so other than that, like everyone should be in a team of 3. And there's already an option in Piazza to find team members. Use that option. And maybe if you want to advertise your team, like to get a third person, you could also do that in the public chat now, like now during the class or in the break and so on. So find your teammates. And I also have some announcement regarding the exam. So the final exam is going to be on the same date as announced by the university. I guess it is December 18th. Can someone correct me if I'm wrong in the chat? Is it 18th or 19th? 19th. Well, I think it was a Saturday. Is it a Saturday? Yeah. So now December 19th. So we are going to have an online exam, and I will probably give more details about the exam next week, or maybe in the Thursday's lecture once I figure out. But you would need access to internet. You would need, you should also know how to scan your answers if you're writing it in hand. Okay, so if I'm sure like you're going to do this for other courses as well, but still I would encourage you to install a good scanning app in your phone or iPad or whatever, and also try to scan things and like make sure that you're submitting a legible answer. If your answer is not legible, we cannot grade that answer. And once the deadline is over, you cannot come back and say, oh, okay, let me give you a clear answer, right? So you have to submit your answer by the deadline. So maybe do a mock by trying to write something and scan it in the paper and see how it is. Okay, so some of the teams are in 2. No, teams cannot be in 2. The teams have to be in 3. And for the Kaggle, the assignment is already released, as in the Kaggle statement is already released. The training data is also already released. You can start working on your competition right now. We will release the test data on Friday. More on exam format in the next lecture. Okay, so we will release the test data the coming Friday, but the competition is already released. Like, so if you are following your Moodle, like you should have already received a Moodle announcement on Saturday, I guess. If you're not checking Moodle, please check your Moodle announcements regularly. Okay, so I think let's continue. Let's start. Let me share my iPad. We can take more questions about assignments and stuff later. Okay, so let's start. So just to give you a quick recap of what we have been seeing so far, like, so we have been looking at ensemble methods, right? Like, which is basically the idea of combining classifiers, right? Like, and so far, so we have seen two approaches. The first one is bagging, and the second one is boosting, right? So the idea of bagging is to just train K classifiers in parallel and take an average of their prediction. On the other hand, like boosting was a bit more sophisticated. Like, so instead of training K classifiers in parallel, like you are training them in sequence and in such a way that the second classifier focuses on the mistakes of the first classifier, the third classifier focuses on the mistakes of the second, and so on, right? So that is and once you finish the sequential training, then it becomes very similar to bagging because you're going to average, but in this case, you're doing a weighted average of all the classifiers. Okay, so now these are the two things that we have seen so far. So now let's try to understand the differences between these two before we move to the next approach. Okay, so we're going to compare bagging and boosting. Okay, so usually bagging is a faster approach. Why? Because you can actually train all the classifiers in parallel, right? Like on the other hand, boosting is slower since it is a sequential process. Okay, even though it's a faster approach, bagging only has very small error reduction. We have seen the reason in the bagging lecture, right? So when you bag, you're reducing the variance, but that is more effective only when the classifier predictions are uncorrelated, right? On the other hand, like since we are doing this bootstrap dataset idea, the classifiers are often correlated, so the error reduction is actually very small. On the other hand, boosting could actually have more error reduction. Okay, now bagging actually works well with reasonable classifiers. Okay, you need to have for to do bagging, you actually need good classifiers, and then you're bagging the performance of these good classifiers. Okay, on the other hand, boosting works with even very simple classifiers. Okay, so we have seen that, right? Like, so the boosting example that we saw was with decision stump, which is like a very simple linear classifier. You take this very simple linear classifier and do boosting, you get nonlinear like decision boundary, right? Okay, so now bagging actually has some issues with lot of mislabeled data. If your data is mislabeled, okay, bagging will have some issues, okay, but it is only relatively less. Okay, on the other hand, boosting, it actually has problem if lot of data is mislabeled. So can someone explain why? Can someone explain why boosting has boosting is severely affected by a lot of mislabeled data? Chat or hand raise? Okay, any answers? Oh, the question. Okay, the question is, if I have a lot of mislabeled data in my task, then I say that boosting is more affected than bagging. Why? Okay, any answers? Yeah, so as some of you rightly point out, the classifier will try harder to label those wrong data, right? Like it will actually start focusing. So the whole idea or principle of boosting is to focus on your errors. So sometimes like when the data itself is wrong, then the model might have the correct label, but the training scenario tells that it is a wrong label because of the mislabeling issues, right? Now, this actually could lead to overfitting. You might be overfitting to the mislabeling in the data set. Okay, now that doesn't happen with bagging. Okay, and bagging reduces variance, right? Like this is something that we have already discussed in the bagging lecture. Okay, now what is boosting doing? Is boosting trying to reduce the variance? No, right? Like, so boosting actually reduces the bias of the extremely weak learners. Okay, so if you use very simple learner, the simple learner is going to have a very high bias. Boosting is a way to combine these high bias models into like something which has reduced bias and hence better performance. Okay, so now these two are like fundamentally different principles, bagging and boosting. Okay, okay. So now before we continue further, like I would like to take a quick detour and talk about cross validation. Well, like maybe we should have discussed this part in the beginning of the course. We missed it, so we are going to have like some discussion on cross validation. Okay, so I think we saw cross validation probably in the second or third lecture, right? Like, so it's basically the idea of splitting your data set into training and validation set, right? So why do we do this? If we are interested in doing model selection, like we will use the validation set to find the best model, right? So now this idea of splitting your data, your entire data into training and valid so that you can use the validation data to choose the model is known as cross validation. Okay, now there is an issue with this cross validation method. Okay, so let's say I give you 10K. Well, now this is something that you're going to directly apply in your Kaggle competition as well, right? So if you've already read the statement from the Kaggle competition, you have 10K training examples, right? And it's a classification problem with 10K training examples, and I did not give you a separate validation set. Now it is your responsibility to come up with your own validation set, okay? Now let's say I split this data into 8K for training and 2K for validation, okay? Now, what is the guarantee that this 2K validation set is actually representative of the test data, right? So what if I chose this 2K, what if I was just unlucky, like certain parts of the data went to the validation and it is not representative of the distribution of the original task, right? Like, so, or imagine I sampled 2K validation set and one class is missing from this, right? It could also happen. If you're randomly choosing 2K, maybe one or two classes will miss from the validation set, right? Like, so now this validation performance is not a representative of the test performance. So how do we resolve this issue? So one way to resolve this issue, which you guys have already done in your assignments, is the idea of k-fold cross validation. Okay, so now instead of choosing a random subset as a validation set, I'm going to divide the data set into multiple parts. Okay, so let's just do five folds for now. Like, so I'm going to divide the data into fold 1, fold 2, fold 3, fold 4, fold 5. Okay, now I'm going to run my algorithm 5 times, each time considering one of these fold as a validation. So now instead of having one validation, we have 5 representative validation, and you average over these 5 validation, that is going to give you a better validation performance. Okay, so now how do I do that? So I could actually, in my first training, I could consider this to be the validation set and this to be the entire remaining portion to be the test set, training set. Okay, you train on the folds 2, 3, 4, 5 and check the validation performance in fold 1. Now in the next experiment, I would actually consider the second fold to be the validation and the rest to be train. Okay, similarly in the third experiment, like in the third run, like, so this is my valid and the rest is train, right? Okay, and the fourth, this is my valid and the rest is train. I'll just put T for train. Okay, and finally this is my valid and the rest is my time. Okay, so now what have I done here? So I have divided the data into k folds, in this case 5 folds, right? I'm using k minus 1 folds for training and kth fold for validation. Okay, and then I just take an average of all k performance. Okay, as you can see, this is actually a costly method. Why is this costly? Because if you have 10 folds, you have to run your experiment 10 times. Okay, okay. Now here is a question. So let's say I'm interested in doing hyperparameter selection. Like, okay, so maybe let's take an example. Okay, let's say we are interested in doing KNN. Okay, now k is the hyperparameter, right? I'm going to try different values of k, and I'm doing k-fold cross-val. Okay, there are two k's, but those two k's are different. So let's say I'm doing 5-fold cross-validation. Okay, and I pick a k which is the best possible k. Okay, now for this particular value of k, I have 5 different models, right? Like, so one model from this experiment, one model from this experiment, one from this, one from this, one from this. Now, which model should I pick? Any idea? So what is the final model? In the end, like, we just need one model, right? So what would be the final model? All of them. How would you use all of them? Okay, so you could do all of them, majority voting. Okay. You could do all of them with bagging. Yeah, that's also, well, that's majority voting too. Like, that's a good answer. But what do you mean by the one with the best validation score? Because our validation score is actually average of 5 validation scores, right? Okay, so I think, okay, the one, well, we don't know the test score. Like, you have to do the model selection before finding the test score. Yeah, so, okay, there are several good answers. Okay, first of all, there is no right answer here, right? Like, so, like, you could do bagging with these 5 models, or you could somehow take an average of these predictions, right? But one common strategy which people often use, like, which is also reported in the chat, is once you find the best K, you retrain your model with all the data set. Now you don't need the validation set because you already found the like best model, then you just retrain. So that is another strategy. Okay. A quick note. So usually when you have like a very small data set, okay, like you have like only 10 examples, 20 examples, or 100 examples to learn from, people do this extreme thing called leave one out cross validation. Okay, which is basically the idea that when you have n data points, you will use n minus 1 data points for training and the nth data point for validation. Like, if you have 10 data points, only 10 data points for the task, you do train with 9, test the 10th, predict the 10th, then train with the next 9, predict the 10th, and so on. Okay, that's an extreme case. Okay, so there is a reason why we did this detour. Okay, so this is going to be useful in the third ensemble method that we are going to see, which is the idea of stacking. Okay, so stacking is also known as stacked generalization. Okay, so now this is an idea by Wolpert in 1992. Okay, so now what is stacking? So as the name suggests, we are going to stack classifiers one on the top of another. Okay, so to be more specific, given the data, I will train k classifiers. Let's just, for example, let's say C1, C2, and C3. Okay, now these classifiers are making prediction, right? Like, if you're doing simple bagging, you would just do majority voting of this, right? Now, instead of doing majority voting, you can actually design another classifier. Okay, we are going to call this classifier as a meta classifier. Okay, this is meta classifier because this classifier is going to take the output of these three classifiers and try to make a prediction y hat. Is that clear? Now these are I'm going to call these as base classifiers, like how we call in bagging and boosting. Okay, this is a meta classifier. Okay, now unlike bagging and boosting, which kind of expects the same type of classifier, okay, you can actually have different classifiers as base classifiers. Just to give you an example, my C1 could be naive Bayes. Okay, my C2 could be K nearest neighbor. My C3 could be SVM. I could have a C4, which is logistic regression. Okay, you could have any type of classifier you want, and all you need is just the output of these classifiers so that you can actually learn another classifier. Okay, now how do I train such a system, right? Like, so training these three classifiers is simple. C1, C2, C3, you take the data, you train it, it has prediction. Okay, now how do I train the meta classifier? Okay, now let's start with one simple strategy. The strategy here is, let's say I have a training set. Okay, let's say I have 100 examples in my training set, a bunch of X, Y. Okay, I'm going to use this training set to train C1, C2, C3. I have 3 trained classifiers. Okay, now I'm going to use these trained classifiers to construct the data set for training my meta classifier. Now, how am I going to do that? I will take the X, I will pass it through C1, C2, C3. Okay, so now instead of putting X, let me put, I'll take the entire data set. I'll pass it through C1, C2, C3. Okay, now C1 is going to give me the prediction 1. C2 is going to give me prediction 2. C3 is going to give me prediction 3. Okay, now I'm going to create a new data set. This new data set has features P1, P2, P3, and the target Y. Okay, this is for the first example. Similarly, for the second example, P1, P2, P3, the outputs of these 3 classifiers as the features and a target. For if I have 100 examples, right? So 100 examples. Okay, now I'm going to use this data set to train a meta classifier to make prediction Y. Okay, now this is my, now once I have this classifier trained, then at inference time, I would take the data, pass it through all the 3 classifiers, get P1, P2, P3, pass P3 to meta classifier. Meta classifier is going to give me the answer. Okay, now this setup that I have described has some issue. Can someone find what is the issue? Any hand raised, chat? Well, I really like to hear some voices. So if you don't mind answering by hand raise, please do that. Now, what could be the potential issue with this setup? Any answer? Okay, it has a high bias. What do you mean by that? What is the bias? Okay, we are predicting with the training data set. Now, why is that a problem? It's not the proxy, you could overfit. Okay, so you are all moving towards the right direction. Okay, now let me maybe explain that. Okay, so some of you said it's high bias, some of you say it might overfit. Some of you say it's not a good proxy, right? They are all reasonable answers. Let me tell you why. For example, okay, so the main issue that as people rightly pointed out is we are just dealing with the training data here, right? So we have to be very careful. So for example, let's say my classifier 1 has 40% performance. Classifier 2 has 85% performance. Okay, and classifier 3 has 50% performance. Okay, this is the training performance, right? Now, I want to predict the training label. Why? By using this meta classifier. Now, what is the weight? Like, how would the meta classifier weight these classes C1, C2, C3, classifier C1, C2, C3, right? So it is going to give high weightage to C2, right? Because C2 is already 85% correct. So if I just follow C2, the meta classifier can also get 85%, right? So the simple strategy for the meta classifier is to give high weightage to C2. But we don't know the generalization performance of C2, right? C2 might actually have a very bad generalization performance. Maybe this is overfitting, right? And we don't have any clue about whether the model is overfitting or not. And hence, this whole setup has this issue that meta classifier might overfit to a classifier which doesn't generalize well. Okay, now how do I resolve this issue? So this is why I introduced K4 cross-validation. Okay, so now how do we resolve this issue? So what we are going to do is we are first going to divide the data into K folds. Okay, now I take the data set, I divide it into, let's say 5 folds, 1, 2, 3, 4, 5. Okay, now for the classifier 1, okay, we are just going to deal with classifier 1. So what I'm going to do is I'm going to train this classifier by using the first 4 parts, okay, and make predictions for the 5th part. I'm treating 5th part as a validation, okay. Then in the next step, I'm going to consider this to be my prediction part and use the rest as a training. Okay, similarly, this is my prediction and the rest is training for the rest, right? So I'm going to create a new data set. Okay, and this data set is going to have 5 parts. Okay, now for the last part, I would copy this prediction. For the second last part, I would copy this prediction. For the third part, I would copy this prediction. Okay, and I will have the corresponding Y. This is my X, which is basically P1, P2, P3, and then there's Y. Is that clear? So what have I done here? I have created a new data set, okay, which is not the training predictions. They are actually validation prediction, but I don't have a separate validation set. So I just used the K-fold cross-validation hack, and whenever I was predicting an example, I made sure that the predictor did not see that example before. Okay. Now, if I create a new meta classifier by using this data set, if the meta classifier has high performance, what does that mean? Sorry, maybe I'll put it in a different way. If the meta classifier gives so much importance to one specific classifier, what does that mean? It just means that that classifier is good in generalization. Is that clear? So any questions about, so this kind of concludes our discussion on ensemble methods. Like, so any questions about stacking or ensembling in general?
There was this question before, which asks, what happens when there is high deviation in validation performance across K-folds? Is the problem
Okay, so
with the
when you
data
have
set?
high deviation in validation performance across K-fold, it just means that your distribution, the distribution is still not Perfect, right? Like so maybe you have to change your sampling strategy. So we don't cover that much in detail, like, but like you could go check for things like stratified sampling, which is basically the idea of like coming up with a validation set which has exactly the same training distribution as the training set, right? Like so there are better sampling strategies available to avoid this. So there's a question which is X here is only the one feature. Okay. Okay. X here, if you have three classes, then X has three features: prediction of class one, prediction of class two, prediction of class three. Is that clear? Okay. Any question before we start a fresh topic? Any other questions? Okay, so I guess, okay, that concludes our discussion on ensemble models. And this is especially for Kaggle competitions, like ensembling is like one of the main like trick or useful tool to have in your like code to actually get the final 1% or 2% improvement over your competitors. Okay, so I'm sure you will all be using these ensemble methods in your Kaggle competition. Okay, so now let's continue. So we are going to, okay, so if you remember, like we were discussing about various ways of doing classification, like before we started discussing ensemble methods, right? Like so we looked at, we started with basic logistic regression, like GDA logistic regression, and then like we discussed about perceptrons, max margin classifiers. We have discussed k nearest neighbors. We have discussed decision trees, right? So we have discussed a lot of classification algorithms. So today we are going to discuss yet another classification algorithm, which is neural networks. Okay, well, probably I don't need, oh, sorry, probably I don't need the chapter number. Okay, neural networks. Okay, now there are many ways in which, okay, so given the foundation that we have so far, there are actually many ways in which we could move to neural networks. We could move to neural networks from logistic regression, or we could move to neural networks from perceptron. Okay, so there are many ways in which we could move to neural networks from stacking, right? Like, so there are many ways in which we could come to neural networks. But I'm going to take a historic approach here, okay, just to tell you a bit of history. So we will start with the infamous XOR problem. Okay, so this is during 1969, okay, the famous work or infamous work by Marvin Minsky and Papert. Okay, so if you remember, perceptrons were introduced in 50s, and when perceptrons were initially introduced, just like how we have like media hype for deep learning and artificial intelligence, like there was like its own media hype. Newspapers reporting, oh, perceptrons can do anything that we want. It is the artificial general intelligence and so on. Okay, now after 50 years, we know that perceptrons are such a simple classifier. They can only model linear decision boundaries, so it's a linear classifier, right? Like, but there was no such fine understanding then. Okay, and when people were thinking that perceptron is the universal learning algorithm in 1969, like so Minsky and Papert, like two researchers, like they came up with this book on perceptron, which actually was with the aim of trying to analyze the shortcomings of perceptron. Okay, so in that book they discussed the famous XOR problem, like which you guys might have already seen in your Boolean algebra or digital circuit courses, right? Like so, like if you don't know XOR problem, it's a very simple problem where like you have two inputs, x1 and x2. Okay, the output is XOR. Okay, so when both the inputs are 0, your output is 0. When exclusively one of them is 1, your output is 1. Okay, if both are 1, the output is 0. So this is the XOR problem. Okay, Now, this is a very, very, very simple problem, right? Like, so it's like a simple toy problem, and Minsky and Papert showed that perceptron cannot solve this problem. Okay, and their book said, oh, they cannot even solve this very simple XR problem, so they cannot solve real life problems. Hence, they are not very useful, right? Like, so I think later Minsky mentioned that the goal of the book was not to trash perceptron, but just to have a scientific understanding of what is happening and how can we improve. But to some extent, the book discouraged researchers working in perceptrons and related algorithms. And it has become a trend that people don't work on these kind of learning algorithms because they thought, oh, Minsky's book shows that this algorithm will not work and this direction is not useful, so let's not work on this, right? So now, in some sense, like it created like a winter for research in that direction, like because no one was working on this, all because of this very simple problem. Okay, but now with all our like understanding, like we know why XOR problem is not solvable by perceptrons. Okay, to understand that, let's first plot the data. I have x1, x2, okay, 0, 1, 0, 1, 0, 0, 0. This is 1, this is 0. Okay, so once you plot the data, it is actually very easy for us to now know that this is not solvable by a perceptron. Can someone tell me why? So why is it not possible? Yeah, so this is not a linearly separable problem, right? So in fact, if I have to divide zeros and ones, I cannot draw a line. If I draw a line here, that zero is misclassified. If I draw a line here, that zero is misclassified, right? So I need something nonlinear to divide this, right? So now perceptrons, we know that perceptrons are linear models, so they cannot solve this problem, right? Okay, now how can you solve this problem by using perceptron? I'm telling you that perceptron is the only classifier you can use, and I want you to solve this task. How can you solve this problem? Any idea? Yeah, so we have already seen in previous lectures the basic but powerful idea of nonlinear basis functions, right? You can take any linear classifier which takes x, okay? You just add a nonlinear basis function, a fixed nonlinear basis function. Now this whole thing becomes nonlinear, right? So that's the beauty of nonlinear basis functions. So in fact, I can actually come up with a nonlinear basis function for this particular toy example, okay? So the two features I'm going to design, the first one is AND of x1, x2 bar. The second one is AND of x1 bar, x2. If you already know Boolean, like if you already know the basics of logic, like you know what this is. If you don't know, it's fine. Like it's not very important for, it's not very relevant for the discussion. Okay. Okay. So now the moment I come up with these two basis functions, phi1 and phi2, okay, I divide the data into like 0, 0 is 1. The other 0, 0 is also lying nearby. Okay. So now you can see that this has suddenly become a linearly separable problem, right? So I can just draw a line and divide this, right? So now the perceptron can actually solve this problem in this space, right? Okay, now what is this basis function doing, right? So what is this basis function doing? So like what the basis function has done, at least here, is it took this data set which was not linearly separable, and it projected into a space in such a way that the data set became linearly separable. Okay, so basically the basis functions, they project the data from the original space to a new space, okay, where it might be easy to learn to classify. Okay, or in other words, basis functions actually change the representation of the data. Okay, however, it is very crucial to choose a specific basis function, right? Like, so what basis function you are choosing matters. If you choose a wrong basis function, then the problem might become even harder or not solvable, right? So there is a lot of effort needed in choosing the basis function. Okay, now while it is easy for the XOR problem, it's not very easy for complex problems. Okay, so now, like, before we continue further, like, let's actually try to visualize the whole thing. Okay, so now I have x1, x2. Okay, what is perceptron doing? Perceptron is just multiplying this with w1 and this with w2, and it makes a prediction, right? So this is perceptron with original input, right? Now, instead of this, if I use a basis function, then I would have phi1 and phi2 passed to the perceptron, and this is w1 and w2. Okay, now this is the perceptron with basis functions. Okay, now w1 and w2 are the parameters here, right? So now I can actually take this second diagram and expand it even further, okay? Because originally what I have is x1 and x2, right? So now my basis functions phi1 and phi2 essentially take my x1 and x2 as input and does some nonlinear computation and then pass it to the perceptron, right? Okay, so now if you look at this part, this is fixed. You could use a sigmoidal basis function, or you could use a Gaussian basis function. You could use a polynomial basis function. You could use whatever basis function you want, right? Like, so now this part is fixed. Now you have the second part, right? So this is my classifier. Okay, now this is the fixed part, which is responsible for the representation. Okay, and this is my classifier. Now this classifier has parameters W1 and W2. Okay, now for this particular XOR problem, I chose phi1 and phi2 in such a way that the task becomes easier, right? As I said before, it is not possible for you to manually design these basis functions, okay? So now we are going to take a machine learning approach, okay? So since we are trying to learn everything, like, why not learn the representation as well? Like, why does the representation has to be fixed, right? Like, so what if I learn the basis functions? Or what if I learn the representation? Okay, so now this idea is actually known as representation learning. Okay, now this actually involves adding parameters to my representation layer. Okay, now I can actually have, for example, v11, v12, v21, v22. I can add parameters here. Okay, and now I can also learn the parameters of the representation layer. Is the idea clear? Okay, so now let's actually discuss a bit deeper about this. Okay, so I have x1, I have x2, and my projection layer is phi1 and phi2, right? So now instead of having a like fixed basis function, like, I'm actually going to learn these two as v11, v12, v21, v22. Okay, now
Excuse
then,
me.
yeah.
Before going further, Mercedes is asking for more explanation on the
Yeah,
previous
that's what I'm
point.
doing now. That's what I'm doing now.
Thanks.
Okay, so W1 and W2, right? So what have I done here? So now we have this layered model where we are going to call this input as the input layer. Okay, so then we make a projection, right? So this is my projection layer. So finally, this is my classifier layer. Classifier, or we could also call that as output layer. Okay, now these parameters W1 and W2 are my classifier parameters. Okay, the parameters that I have here, V1, V2, V11, V12, right? These are my projection parameters. Okay, so from now on, instead of using a fixed basis function, we are going to learn the basis function as well. Okay, so along with the classifier parameters, we will also learn the projection parameters by minimizing the error function. Is that clear? Okay, now this model, right? Like, so the new model that we have so far. So if you just look at the second half, that is my usual perceptron. Like I have just added an extra projection layer before the perceptron, right? Like, so now this layered architecture has a name. So this is also known as multi-layered perceptron or MLP. Okay, and there is also a biological inspiration for this. Like you could consider these individual units as neurons, artificial neurons. Okay, and this whole network structure as a neural network. Is that clear? Now the projection layer, which is in between the input layer and output layer, right? So what is the use of this projection layer? So we don't have the final use for the projection layer. So the projection layer is only there to change the data from one space to the other space so that it becomes easy for the classifier, right? So now this layer is often called as the hidden layer because its only job is to support the classifier. Okay, it's hidden because we only care about the final layer, not about the intermediate layer. Okay, okay, now this is neural networks. Of course, we are going to see how to learn the parameters of this architecture and so on. But any questions before that? So we will also stop here for a break. So any questions?
There was this question by Guy Herman, which asks, neural nets are only used for classification or also for regression?
We could also use it for regression. We will see that. Any other questions? So this actually requires some shift in your thinking. Okay, so far we were just focusing on classification algorithms, right? Like, so we were taking the features for granted. Either the features were given to us or someone gave us the nonlinear basis functions, right? Like, so now we are slowly upgrading our classifiers by saying that, oh, okay, if the features are not good enough, I will learn my own set of features by projecting the data from the input layer to the projection layer so that it becomes easy for the classifier. Okay, now this whole architecture is nonlinear. Okay, so this is a nonlinear model. Any questions? Okay, so if there are no more questions, like I'm going to stop the recording and we will go for a short like we'll go for a break, so we'll resume at 1:45.